Okay, welcome back. Sorry for the delay. Okay, we got two people. All right, well, this is the plan that I got for today. Is obviously I'm going to finish the chapter 14. I'm looking at the schedule here. Today's the 20th, so today we'll finish up chapter 14, which is maybe about 4 or 5 slides, and then we're just gonna call it a day. And then Thursday, no class on Thursday. We have Thanksgiving. And then next Tuesday, which is the 29th, I will continue with chapter 15, which is about 10 slides. That also is a fairly short chapter. And then after that, the plan is that's the 29th. Then that Thursday on the 1st, we have a study day, so you come in for questions. Exam number 5 is on the 6th. We will probably be done with chapter 15 on the 29th. But if we're not, we'll finish it up on the 6th for sure. So either way, even though it's not listed, the 6th will also probably be another study day, okay? Which includes on the 8th. So this is one of the advantages of doing lectures online during exam day. We get done ahead of time, which leaves the last 4 or 5 days to Zoom days for you to come in with questions and go over problems for anything. So on the 13th is the end of the semester. And that's when we do the final. It will be, I mentioned it before, but I'll say it again, 60 questions, 60 questions, all multiple choice, 110 minutes, it's timed. What else? Comprehensive, covers all the chapters. Probably roughly approximately, I don't know, 3 to 4 questions per chapter, ballpark. Questions very similar with the multiple choice questions you've seen before in the other exams. I will also open up, I got to get permission to do this, is open up exams 1 through 5, so you can go back and use them for review, okay? I need to get the okay because those are exams that are created by the department. All of us had 2 cents in it, but it's one of the things. So once I find out, probably on the week of the 5th, I will probably, if I get permission, open up all the previous exams, excluding number 5. Obviously, you got to wait till you're done with it. So probably on the 7th, I'll open them up, and then you can use that for, excuse me, I got to sneeze. Okay, use that for reference. Also, study guides. We also have a practice final exam on the course website. It's also in your final module. You can use that as a reference for the exam. Let me see what else. Yes, on the 13th, that is the last day I can offer anything. So the exam, I can move the exam, but I can only move it forward only a couple of days. I can't move it after the 13th. So check your schedules. You got a whole, 3 weeks from now. Oh, more than that. What am I saying? A month from now of checking your schedule, making sure you allocate the time necessary to complete it. Okay, because I can't change it until after the 13th, but I can move it forward maybe from the 11th to the 12th if your work schedule or whatever other schedule you have prevents you from doing it on the 13th. Okay. Let me see what else. Excuse me. Since the 13th is the last day, if you have any assignments you did not turn in, I've mentioned this before, all assignments that have been missed are still open I'm talking about activities and homework only, not the exams. So you can go and do them, and unfortunately, there is still a penalty associated with it, but nevertheless, some points is better than no points. And then finally, the homework. If you did those assignments, you have 2 attempts. You only did the one attempt, and for whatever reason, you want to go back and you want to improve your grade on that homework assignment. By all means, you're more than welcome to do that. But what will happen is you go back and do attempt number 2, and then Canvas will treat it as being late. And then even though you score higher than the first exam, the first attempt, it will penalize you. So if you do that and you did the first attempt in the time scale when it was due or the day of or before, then I will go back on your second attempt and remove the penalty if you give you a better grade if you did the first attempt in the proper due date. Okay. All right. I think I got it all covered here. So any questions you may have? Yeah, if you do, you just shoot me an email and we'll take care of it. Let's see. The activity, yes, all the assignments except the exams do get a late penalty involved. So now, if you had a legitimate excuse for missing that activity, I do look into that. If it's legitimate, I will remove the late penalty. So, okay. So if you have one that's late and you get a late penalty on it and you get a plausible reason behind it, I have no problems removing the penalty. Unless I had one student wanted to know if I take the penalty off because evidently it was their birthday and they went out and celebrated, and I guess he got pretty hammered. And they wanted to know if I could take the late penalty off because he didn't do the homework.
Professor, I'm
Yes.
sorry.
No.
You saying I see an email saying that we have some problem with the latest activity.
Yes. Yes. We got it repaired, and basically we removed that's activity for chapter 14. What it was is it has to do with the hand sanitizer activity. What it was a video that the link went to the American Chemical Society, and the American Chemical Society changed the link and gave you something about gummy bears. So what we did is we just removed that question, and then so you don't have to worry about it because that original video disappeared, and we were trying to find it and we couldn't find one that's suitable. So yeah, if you did do it and you were getting a crazy link, let me know, and I'll go in there and correct the points and so forth for you. But
Thank
I
you.
fixed it yesterday. So if you haven't done it yet, you shouldn't have any problems. There's basically now just 2 questions.
Thank you.
Sure, no problem. All right. All right. So anyway, any other questions? Yeah. Well, I'll tell you what, let's knock this out. Really, we're going to be done fairly early. It take about half an hour, if so. I don't know, something in my house all of a sudden started making me want to sneeze. Oh, my eyes got all puffy. All right, so we've been talking about intramolecular forces, okay? And I think what we need to make sure we fully understand is when we're talking about intramolecular forces that we are dealing with. This represents 2 compounds here, and we are looking at the interaction right here IMF, intermolecular forces that these two species, whatever it may be, are doing with each other, interacting, these intermolecular forces. So some of these, and we had three of them, three of these forces. We had the London dispersion forces, we had the dipole-dipole forces, then we had the hydrogen bridging force, and then we had the ion dipole force, okay? Now, the ion dipole force deals normally with an ionic compound in an aqueous system, an H2O. Okay, so if the question doesn't mention anything about ionic compounds or anything of the sort, then this force is not involved. Now, the other forces here deal with covalent compounds. Okay, and as you recall, obviously, hopefully, we know now that we have two types. We have non-polar covalent compounds, covalent compounds, non-polar and polar. Okay, and so we need to learn to identify the molecule and assign it as to whether it's polar or non-polar. Okay, once we do that, once we assign the polarity of the molecule, then we can assign an intermolecular force. So London dispersion forces deal with non-polar molecules. Okay, non-polar molecules for London dispersion forces. For the dipole-dipole forces and the hydrogen bridging forces, they are polar molecules, okay? But for those molecules that contain hydrogen that are bonded to nitrogen, oxygen, or fluoride, they have their own special dipole. It is a dipole, okay? For example, a bond between a hydrogen chloride and a bond between a hydrogen and fluoride. Both of them are a dipole. Both of them have a dipole going from the hydrogen to the chloride, okay? But the fact that this hydrogen is bonded to fluoride gives it an extra strength, an extra force that has its own unique name, which we call hydrogen bridging force. Whereas the other just straightforward without hydrogen, without nitrogen, oxygen, or fluoride are simply dipole-dipole. Okay? Dipole-dipole forces. They are both dipoles, there's no question about it. But the hydrogen bonded to fluoride, nitrogen, and oxygen have an extra property, an extra strength. And we give it their own unique name, which is hydrogen bridging. All right. So once we determine if it's nonpolar, we assign it London dispersion forces because all nonpolar molecules, the only force they have to deal with is London dispersion forces. Now, we have to remember how to define a molecule as nonpolar, because if you have all nonpolar bonds, okay, like carbon-hydrogen bonds, then it is a nonpolar species. All the diatomics are nonpolar, okay? And if you have polar bonds that cancel each other out in the molecule based on the geometry, which here comes the Lewis dot structures, based on the geometry it has, and the dipole, the polar bonds cancel each other out, we end up with a nonpolar compound. Recall that we did carbon dioxide. Okay, carbon dioxide has two polar bonds that go in opposite direction. Okay, two polar bonds that go in opposite direction results in the polar bonds canceling each other out, resulting in a nonpolar molecule. All right, so we have to learn how to assign the polarity. From that, then we learn to give it a specific intermolecular force. And then from that information, knowing that the strength, HBF is number one, London dispersion forces are weaker of the three. We're doing a relative strength. HBF is the strongest, followed by the dipole-dipole, and then the weaker of the bunch is the London dispersion forces. Once we know that, and we assign them that particular force, we can do a compare and contrast between molecules. We can now look at them, determine the structure of each molecule, and say, well, this one's going to have a different physical property, a higher physical property than this one. Okay? And when we looking at that, we're not talking about the bond that's in here, okay? We are talking about the intermolecular force. And we're talking about energy that we put into the system to break up that intermolecular force. And if that energy is high, a lot of energy, that implies that that force is pretty strong. Since hydrogen bridging force is the strongest, it's going to require a lot of energy relative to the dipole-dipole and London dispersion forces to break up that interaction. And so that results in what we call boiling point to be higher because it takes more energy to break up that interaction. All right, so what we do here is they want to do a comparison. Let's compare ammonia and fluorine, all right? Well, before we do that, we have to know the structure. And we are dealing with fluorine, which is a diatomic species, okay? So we have F2, okay? Another way to write that is just fluorine bonded to fluorine, and then we have the Lewis dot, the pair of electrons around, if you recall how we did the Lewis dot structure. Since it's diatomic, okay, we have a non-polar compound, non-polar. Since it's non-polar, we can automatically assign to it London dispersion forces, okay? Because again, all non-polar species have London dispersion forces. Ammonia is the other one, which if you haven't learned its structure, you might, there's formula, you may just want to put this to memory, is N nitrogen with 3 hydrogens bonded to it. And if you recall, we had done the Lewis dot structure. Nitrogen is a central atom. And we came up with this following structure, Lewis dot structure, with a pair of lone electrons on the central atom, which, as I told you before, once that shows up, automatically polar species, okay? Polar species. And so this is a polar compound, okay? Then we look further and we see the combination of a nitrogen-hydrogen bond, okay? Nitrogen-hydrogen bond. So we can assign to it hydrogen bridging force, okay? So now, once we've done that, we can answer questions concerning these two molecules and do some reference comparison with respect to the physical properties of boiling point, okay, vapor pressure, surface tension, and viscosity. Okay, we can't give you absolute numbers, but we can do comparison, relative comparison between two molecules. All right, so that's how we attack the problem. We come up with the formula, okay? From that, and knowing the polarity of the molecule, then we assign their specific intermolecular force. So then we can answer some questions. For example, which has the stronger IMF? Well, obviously the hydrogen bridging force does, right? As we talked about earlier. So ammonia has the stronger IMF. And that should kind of trigger that down the road, that since it has a higher IMF, it's going to take more energy to break apart this force, which means it's going to have a higher boiling point, for example. which has a lower boiling point. Well, just the counter of what we just talked about, London forces are the weakest. So therefore, it takes less energy to break up that interaction between the molecules. So in this scenario, fluorine would have the lower boiling point compared to ammonia. Okay, which is polar? Well, we went through that earlier, trying to determine what force to give it. And ammonia, obviously, is the polar species. Okay, and then which has the higher vapor pressure. Remember, the vapor pressure is you have a liquid in a closed container. So you're going to have two phases. You're going to have the liquid phase, and then on the top is the gas phase. And if you think about this again, if the molecules are being attracted to each other tightly relative to another species, then there's going to be less of those going into the gas phase. So that would cause the vapor pressure to be less, right? So in this case, fluorine would have the higher vapor pressure, okay, because it has the weaker of the force. And so it wouldn't take much, let's say this is a closed container and we got fluorine floating around in here in solution in a liquid phase. And then because it has the lowest of the forces, we're going to have a lot of fluorine in the gas phase compared to ammonia, where we're going to have, yes, there'll be some vapor pressure, but obviously not as much as fluorine. Okay, there'll be less gas molecules up there, hence less pressure. All right, which is the least viscous? Okay, which one flows a little bit better? Okay, that would be fluorine. Okay, because again, they have the weaker force. Now, we're talking about a particular compound, but you can reverse it, go the opposite direction, and compare. For example, you can have I used this example before where I said the flow between, let's say, an oil, maybe a heavy 30-40 weight oil versus water. Put them in a cup, empty them, see who's going to empty the cup first. Well, the water will, okay? Because the water is less viscous than that 30-40 weight oil. So what does that infer about intermolecular forces? Well, that tells you that for the oil relative to the water, because the oil is flowing much slower, those intermolecular forces must be greater, okay, for the oil than the water, okay, because of the flow, the viscosity, I should say, which has more surface tension, and ammonia would have the higher surface tension, again, because in the reasoning, again, the molecules are holding on to each other with greater strength. All right, so this basically what summarizes here. As we increase the IMF interaction, okay, the viscosity increases. Okay? And as what also increases is the boiling point and the surface tension. Again, because the forces to hold the molecules together are very strong relative to another IMF. Okay, the viscosity and the vapor, not vapor pressure, the boiling point and the surface tension increase accordingly. But because of that, the vapor pressure decreases because more, if we're comparing it in the liquid phase, more of these molecules want to stay in the liquid phase rather than go into the gas phase. It doesn't mean it won't do it, but it takes more energy. to put those molecules into the gas phase. Okay. Now, the question could be asked the opposite. As IMF decreases, what happens to viscosity, boiling point, etc.? So here, the question is asked, with the increase in mind with respect to IMF. All right, so just a quick few notes about water. Water is a very, very, very interesting molecule. A lot of research has gone into, you would think, something that's common for us at least. It's all around us, it's in our body, it's just all around us. Very crucial for the way water reacts to the environment, to temperature. Okay. If there was a subtle change in its physical properties, life as we know it probably wouldn't exist. Anyway, water, we done the Lewis-Dot structure. It's given there. It has two bonding electron pairs and it has two non-bonding pairs. Very, very polar, extremely polar. It will dissolve most any ionic compound. Yes, based on the solubility table, compounds are either soluble, 100% ballpark, okay, or insoluble. But doesn't mean it's 0%. Okay, it just means 1 to 5%. So water will literally dissolve anything, especially over time. Over given time, even this desk I have here would eventually dissolve if it was left to the environment of water. All right, so very strong hydrogen bridging forces between the molecules. All right. Now it has a high IMF, very polar as I stated, low vapor pressure, okay, and relatively high boiling points, 100 degrees for boiling point, 0 degrees for melting point. Extremely high surface tension. Well, actually, extremely high surface tension. And one property about water, which is unusual with other liquids, is that when they freeze, it actually expands, okay? And that the density of ice is actually less than the density of water itself, which allows it to float. That's why ice cubes float. Is because the water molecules, the structures themselves, the crystal structure of ice is almost hexagonal here in shape. You see if you look at the left side. So very structured, very ordered. And the overall volume increases. Okay, not a big giant increase, but enough to change the density. And then supposedly on the right-hand side, you see a snowflake, and supposedly no snowflake is supposed to be the same. So I don't know that for sure. That's what you read. Okay, well, let's talk about a heating curve, and we've got a couple slides here, and then we're done for the evening. Okay, all right. What do we mean by the heating curve? Well, we have a graph here, which we have temperature on the y-axis. Okay, we have a scale. Okay, and then we put energy, heat into the system. Okay, and we have a scale. So if we start off at 0.00, we didn't put temperature in the system or anything. And then we can maybe notice initial temperature, put 0 energy. We have this point right here. All right, so we add an X amount of energy, temperature goes up, right? So we collect data. We have data points. The result is that we have a graph that looks like as so. Okay. Now, the interesting thing about this thing is as we're heating matter, giving matter energy, where temperature is going up, we have two plateaus that are observable. One is a plateau when there is a physical change of solid going to liquid. And then we have a second plateau at a given temperature. Okay. All right. And where we have a second plateau where again, There is no increase in temperature as you know, as we put energy into the system. Notice anywhere else, there's a rise in temperature as we put energy, a very steep rise, right there, and then initially, okay, very steep rise up in this region, and this region, okay. But these plateaus, you know, we put more energy into it, and nothing happens. So, what exactly is going on? I'm glad you asked. 1 second here. All right. So what is going on is the following. And this could be an example, you know, this could be water, right? But it can be most anything. So we're at a, let's say 0 degrees and 100 degrees. All right. So below 0, we got solid, obviously it's frozen ice. Now we start putting energy into the system, and the temperature starts to go up, okay? Now, in that rise and that run, the rise and the run, okay, called the slope here, it's all solid, okay? Till we hit the first plateau. We hit the first plateau, then that solid starts to be converted to liquid. And we continue to heat and put energy into the system. And then nothing happens until all of that solid has been converted to liquid. And then we see another increase in temperature. Okay. So the first plateau could be 0 degrees Celsius, for example. That is the melting point of ice. So below that, it's frozen solid. And then we come up to 0 degrees, and then that compound water does a physical change from solid to liquid. When all solid has been converted, then the temperature increases, and guess what? We hit a second. On that rise, it's all liquid until we reach the boiling point. And that is the temperature in which a liquid gets converted to a gas. And we hit a second plateau. And we continue to heat energy, but there's no increase of temperature. It stays at a plateau. On the plateau is where all that liquid that came from here is being converted to vapor into the gas phase. When all of it has been converted, we have another increase in temperature, where goes up to infinity, where it's all gas. So the two plateaus are here. First plateau is where the solid is being converted to liquid. Second plateau is where the liquid is being converted to gas. It is at these plateaus that if I were to draw say, two circles here that represent H2O, okay, the IMF, which is hydrogen bridging force, is pretty hefty. Is it going on here? So what's going on is all the energy that I put into the system is going into breaking up that IMF to kick it into the next phase, okay? And there's no increase in temperature. We are not, I repeat, we are not breaking bonds, That's important. We are not breaking bonds here. We are breaking the intermolecular forces that are keeping the molecules together and attracting each other, okay? So it goes to show you here, you can try to do this at home. You're boiling water, you're going to be 100 degrees and it starts to boil. A lot of times people kick up the temperature thinking they can boil that thing a little bit quicker, but you're wasting your energy, okay? Whatever, as soon as your stuff gets to boil, kick that heat or gas, electricity or gas a little bit less. Just maintain the boil, okay? Because you're not going to make that thing boil any quicker. In fact, what you end up doing by putting more energy is that plateau gets smaller, so all your liquid gets converted to gas right away. But save your energy, your water is boiling, and that's where it's going to stay right there. All right, so that is what is happening with respect to these heating curves. And we put all that together, it says that the temperature during the phase change of solid to liquid and liquid to gas, the temperature remains constant. So all of that energy is being utilized to break the IMF interaction, not just for the water example that he gave, but for any molecule that's going from a solid liquid to gas. Okay. You're not breaking bonds. That's important. You'll be totally 100% incorrect. The amount of energy to break a bond is much, much greater than it is to break up the intermolecular forces. All right. So with that being said, congratulations. You are done with chapter 14. Okay. Chapter 14. We got one more to do, and we will do that, like I said, next Tuesday, chapter 5. That particular chapter, we're going to talk about coffee. No, solutions. Solutions. All right, which coffee is a one? All right. So